Good evening. I just finished my hot foods and I'm uploading. I like to watch the Danish evening news 6:30 in 45 minutes. Let's try to finish this. I forgot my can of tomatoes. Yes, I have to check my cell phone.
Warhead designs after 1960 took on the character of model changes, with every new missile getting a new warhead for marketing reasons. The chief substantive change involved packing more fissile uranium-235 into secondary, as it became available with continued uranium enrichment and the dismantlement of the large I-yield bombs. Starting with the Nova facility at Livermore in the mid-1980s. Nuclear design activity pertaining to radiation-driven implosion was informed by research with indirect drive laser fusion. This work was part of the effort to investigate inertial confinement fusion. Similar work continues at the more powerful National Ignition Facility. The Stockpile Stewardship and Management Program also benefited from research performed at NIF. Explosive testing. Nuclear weapons are in large part designed by trial and error. The trial often involves test explosion of a prototype. In a nuclear explosion, a large number of discrete events, with various probabilities, aggregate into short-lived chaotic energy flows inside the device casing. Complex mathematical models are required to approximate the processes, and in the 1950s there were no computers powerful enough to run them properly. Even today's computers and simulation software are not adequate. 72. It was easy enough to design reliable weapons for the stockpile. If the prototype worked, it could be weaponized and mass-produced. It was much more difficult to understand how it worked or why it failed. Designers gathered as much data as possible during the explosion, before the device destroyed itself, and used the data to calibrate their models, often by inserting fudge factors into equations to make the simulations match experimental results. They also analyzed the weapon debris in fallout to see how much of a potential nuclear reaction had taken place. Light pipes. An important tool for test analysis was the diagnostic light pipe. A probe inside a test device could transmit information by heating a plate of metal to incandescence, an event that could be recorded by instruments located at the far end of a long, very straight pipe. The picture below shows the shrimp device, detonated on the 1st of March, 1954, at Bikini, as the Castle Bravo test. Its 15 megaton explosion was the largest ever by the United States. The silhouette of a man is shown for scale. The device is supported from below, at the ends. The pipes going into the shot cap ceiling, which appear to be supports, are actually diagnostic light pipes. The 8 pipes at the right end, 1, sent information about the detonation of the primary. 2 in the middle, 2, marked the time when X-rays from the primary reached the radiation channel around the secondary. The last 2 pipes, 3, noted the time radiation reached the far end of radiation channel, the difference between 2 and 3 being the radiation transit time for the channel. 73. From the shot cab, the pipes turned horizontally and traveled 7,500 feet, 2.3 kilometers, along a causeway built on the Bikini Reef to a remote-controlled data collection bunker on Nauru Island. While X-rays would normally travel at the speed of light through a low-density material like the plastic foam Chanel filler between 2 and 3. The intensity of radiation from the exploding primary creates a relatively opaque radiation front in the channel filler, which acts like a slow-moving logjam to retard the passage of radiant energy. While the secondary is being compressed by a radiation-induced ablation, neutrons from the primary catch up with the X-rays, penetrate into the secondary, and start breeding tritium via the third reaction noted in the first section above. This Li6 plus N reaction is exothermic, producing 5 MeV per event. The spark plug has not yet been compressed, and, thus, remains subcritical, so no significant fission or fusion takes place as a result. If enough neutrons arrive before implosion of the secondary is complete, though, the crucial temperature differential between the outer and inner parts of the secondary can be degraded, potentially causing the secondary to fail to ignite. The first Livermore-designed thermonuclear weapon, the Morgenstern-Davis, failed in this manner when it was tested as Castle Coon on the 7th of April, 1954. The primary ignited, but the secondary, preheated by the primary's neutron wave, suffered what was termed as an inefficient heatonation. Winkensat Smiley 74, 165. Thus, a weapon with a predicted 1 megaton yield produced only 110 kilotons, of which nearly 10 kt were attributed to fusion. 75. 316. These timing effects, and any problems they cause, are measured by light pipe data. The mathematical simulations which they calibrate are called radiation flow hydrodynamics codes, or channel codes. They are reused to predict the effect of future design modifications. It is not clear from the public record how successful the shrimp light pipes were. The unmanned data bunker was far enough back to remain outside the mile-wide crater, but the 15 megaton blast, 2.5 times as powerful as expected, breached the bunker by blowing its 20-ton door off the hinges and across the inside of bunker. The nearest people were 20 miles, 32 kilometers, farther away, in a bunker that survived intact. 76. Fallout analysis. The most interesting data from Castle Bravo came from radiochemical analysis of weapon debris in fallout. Because of a shortage of enriched lithium-6, 60% of the lithium in the shrimp secondary was ordinary lithium-7, which doesn't breed tritium as easily as lithium-6 does. But it does breed lithium-6 as the product of an N2N reaction, 1 neutron in, 2 neutrons out, a known fact, but with unknown probability. The probability turned out to be high. Fallout analysis revealed to designers that, with the N2N reaction, the shrimp secondary effectively had 2.5 times as much lithium-6 as expected. The tritium, the fusion yield, the neutrons, and the fission yield were all increased accordingly. 77, as noted above. Bravo's fallout analysis also told the outside world, for the first time, that thermonuclear bombs are more fission devices than fusion devices. A Japanese fishing boat, Daigo Fukuri Maru, sailed home with enough fallout on her decks to allow scientists in Japan and elsewhere to determine, and announce that most of the fallout had come from the fission of U-238 by fusion-produced 14 MeV neutrons. Underground testing. Subsidence craters at Yucca Flat, Nevada test site. The global alarm over radioactive fallout, which began with the Castle Bravo event, eventually drove nuclear testing literally underground. The last U.S. above-ground test took place at Johnston Island on November 4, 1962. During the next 3 decades, until September 23, 1992, the United States conducted an average of 2.4 underground nuclear explosions per month, all but a few at the Nevada Test Site, NTS, northwest of Las Vegas. The Yucca Flats section of the NTS is covered with subsidence craters resulting from the collapse of terrain over radioactive caverns created by nuclear explosions. See photo. After the 1974 Threshold Test Ban Treaty, TTBT, which limited underground explosions to 150 kilotons or less, warheads like the half-megaton W-88 had to be tested at less than full yield. Since the primary must be detonated at full yield in order to generate data about the implosion of the secondary, the reduction in yield had to come from the secondary. Replacing much of the lithium-6 deuteride fusion fuel with lithium-7 hydride limited the tritium available for fusion, and thus the overall yield without changing the dynamics of the implosion. The functioning of the device could be evaluated using light pipes, other sensing devices, and analysis of trapped weapon debris. The full yield of the stockpiled weapon could be calculated by extrapolation. Production facilities. When two-stage weapons became standard in the early 1950s, weapon design determined the layout of the new, widely dispersed U.S. production facilities, and vice versa. Because primaries tend to be bulky, especially in diameter, plutonium is the fissile material of choice for pits with beryllium reflectors. It has a smaller critical mass than uranium. The Rocky Flats plant near Boulder, Colorado, was built in 1952 for pit production and consequently became the plutonium and beryllium fabrication facility. The Y-12 plant in Oak Ridge, Tennessee, where mass spectrometers called calutrons had enriched uranium. Fourth Manhattan Project, was redesigned to make secondaries. Fissile U-235 makes the best spark plugs because its critical mass is larger, especially in the cylindrical shape of early thermonuclear secondaries. Early experiments used the two fissile materials in combination, as composite POI pits and spark plugs, but for mass production, it was easier to let the factories specialize. Plutonium pits in primaries, uranium spark plug sound pushers in secondaries. Y-12 made lithium-6 deuteride fusion fuel and U-238 parts, the other two ingredients of secondaries. The Hanford site near Richmond, WA operated plutonium production nuclear reactors and separations facilities during World War II and the Cold War. 9 plutonium production reactors were built and operated there. First being the B reactor, which began operations in September 1944, and the last being the N reactor, which ceased operations in January 1987. The Savannah River site in Aiken, South Carolina, also built in 1952, operated nuclear reactors which converted U-238 into Pu-239 for pits, and converted lithium-6, produced at Y-12, into tritium for booster gas. Since its reactors were moderated with heavy water, deuterium oxide, it also made deuterium for booster gas and for Y-12 to use in making lithium-6. Deuteride. Warhead design safety. Because even low-yield nuclear warheads have astounding destructive power, weapon designers have always recognized the need to incorporate mechanisms and associated procedures intended to prevent accidental detonation. A diagram of the green grass warhead steel ball safety device, shown left, filled, safe, and right empty, live. The steel balls were emptied into a hopper underneath the aircraft before flight, and could be reinserted using a funnel by rotating the bomb on its trolley and raising the hopper gun type. It is inherently dangerous to have a weapon containing a quantity and shape of fissile material which can form a critical mass through a relatively simple accident. Because of this danger, the propellant in Little Boy, 4 bags of cordite, was inserted into the bomb in flight, shortly after takeoff on the 6th of August, 1945. This was the first time a gun-type nuclear weapon had ever been fully assembled. If the weapon falls into water, the moderating effect of Thuter can also cause a criticality accident, even without the weapon being physically damaged. Similarly, a fire caused by an aircraft crashing could easily ignite the propellant, with catastrophic results. Gun-type weapons have always been inherently unsafe.